Welcome back, physics fans, and here we are with a ladder lesson for you today. Okay, so we're going to learn about the physics of ladders, and it is interesting because we're going to use static equilibrium. We have and will have to use both the first and second conditions for static equilibrium to solve them. Okay, so it's a I'd say most questions don't need both. Okay, what is the first condition for static equilibrium? Okay, and that's translational equilibrium. So the little bit of review. Okay, and that is the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. And what is the second condition for static equilibrium? That's rotational equilibrium. Okay, and that is the sum of the torques equals 0. But we have to choose a pivot point, and we should tell us where that pivot point is when we do a torque, because the torque becomes 0 for that force at that pivot point. In the above image, there we go, we have a man climbing up a ladder here. The ladder's against the wall, okay? And here's a fully labeled image, right, with the masses of the normal forces. And there's one more thing here that we need to know. There is not, in physics 12 here, there is not going to be, so no friction on the wall. So no question we'll have friction on the wall. It just adds one more force. Okay? That means there is not going to be a force up on the wall holding it from sliding down. You would normally have a force of friction on the wall here holding it up so it doesn't slide down, but we're not going to include that. Not today and not in this course. Okay, so let's identify all the forces that we have here. M1 is the mass of the man, of the climber. Mass 2 is the mass of the ladder. L is the length of the ladder. Okay, and D is uh, distance man is up ladder. Okay, and theta is the angle to the ground, angle to the horizontal. Okay, N2. Why did I do that first? That's the normal from the ground. And there is a normal on the wall. And we're missing one. What am I missing? Good catch. I'm missing the force of friction. It's labeled right there. If there was no friction force, it's just like sitting it on ice. You wouldn't want to stand on a ladder that's on ice. That would just slip right on out if there's no friction there. Okay, so let's draw the free body diagram over here. We have, I've already started with labeling it. Let's just label all the forces. It's a uniform ladder on almost all cases. So there's a force of gravity pulling down, and I'll call it the center of gravity of the ladder. Okay, there's a man climbing on it, so there's the force of gravity of the man. Okay, there is a normal force, we'll just label it as N1. There's a normal force here. I'm going to do these in red because this is at the bottom. Just because I'm going to do this, you'll understand why. N2 is from the ground, and this one is the force of friction. Okay, and if we take a look at the angles, let's go into 300 degree time zoom here and take a look at it. The angles, if this is the center of gravity coming down, it meets right angles with the ground. So if this is theta, then this is going to be the complement of that. So that we'll call that alpha, and alpha is going to equal 90 minus theta. Okay, so this is alpha as well. So if that is alpha, then this is theta. Okay, and this is, if this is theta, then this is alpha, the angle between the normal and the ladder if you needed it, and we do. Okay, and the force of gravity of the man is also going to be at alpha, just kind of like any force of gravity downwards is going to make an angle of theta. So let's label those angles in our FBD, free body diagram. Okay, if this is theta, then this is alpha, this is alpha, this is theta, and this is alpha. So I've labeled all the angles. Now, in a proper free body diagram, we would not be doing angles in here, but in this chapter I allow it. And then there's distances that we could label in here, but in this chapter I allow it. But in the rest of physics and in a proper physics free body diagram, you wouldn't label angles, you wouldn't draw the wall. I don't want any walls drawn. I don't want any floors drawn. Okay, so the angles that I just added would be wrong. Okay, good. Let's zoom out again. So starting with the vertical direction, why? Well, why not? We have sum of the forces in the y is equal to 0. That means the forces up equals the forces down. So the forces up are N2, and the forces down is the force of gravity of M1 and the force of gravity of M2, the ladder and the man. I'm stopping because this is not an actual question. We're just trying to understand the, the theory behind here. Okay, so I'll just highlight that instead. So if we're given the mass of the man and the mass of the ladder, we can find the normal force up. Okay, next we could do the sum of the horizontal. The force of the x's have to equal 0. That means the forces left equals the forces right. And that means there's only two forces in that direction. That means the force of friction on the ground has to equal the normal force of the ladder on the ladder at the wall. So sometimes people don't like writing the normal force, then you just go with the force of the wall. Okay, and just in case you don't remember the formula, force of friction is equal to mu times the normal force pushing those two surfaces together. And in this case, it's the wall, so the force, no, it's not. There's no friction on the wall. It's down here. So the force of friction is going to be equal to mu times the normal force N2. Okay, so there's two little sub formulas here. Let's just understand what's going on. We now have a relationship between the x and the y, just so we can work through it. So if we have these two masses, we'll have these forces, we'll have N2, that gives us N2 down here. So that it brings us from the vertical to the horizontal, that gives us the force of friction, which gives us the normal force on the wall. So these are related. Okay, we'll leave that alone. Now we'll just do the sum of the torques. Sum of the torques have to equal 0, and that means the torque counterclockwise has to equal the torque clockwise. Okay, I notice that I put down here, there are a few possible places for the pivot point. Okay, the logical one that I see is down here. Why? There's two forces there. So that gets rid of two torques out of summing of the 5 torques that are there. There are 5 forces. But another option is putting it up here. That'll be a sum of 4 torques. So it's your choice, but I recommend doing it at the bottom because that means there's only 3 torques. So you take a look at it. The torque of the wall, if the pivot point's down here, the torque of the wall has to equal the torque of the man and the torque of the ladder. And that's where we'll leave it up. The torque of the wall has to equal the torque of the ladder caused by the ladder's weight plus the torque of the man. Okay, that's kind of like, here it is, we have a force here, we have a force there, and a force here. The pivot point's here. So the wall's pushing it this way, and the man and the ladder, there's the ladder going this way and the man going that way. So that's the logic behind it. This will have the force of the wall. Well, okay, one more line. The force of the wall times the length of the ladder times the sine of, and I think that was theta up at the top, has to equal the force of the center of gravity times half the length of the ladder times sine of alpha plus the force of gravity of the man times his distance up, which is d, times the sine of alpha as well. Okay, I'm not going to go any further. I've already gone too far, more than I wanted to. But that's the theory behind it. And then we just work on these formulas and solve the question. Okay, thank you for watching. Subscribe, smash that like button, and yeah, give to my Patreon. Thank you, and okay, thanks.